Good morning. I want to thank you for this opportunity and especially thank the organizers. For about a decade now, I've been trying to encourage people in big history to look at complexity science, and this workshop is just more than I'd ever imagined. What I want to talk about today is complexity theory and David Christian's vision. Because for me, at the heart of big history is David's vision. That is, that our scientific origin story could function like the myth of more traditional societies and provide the shared map that shows us how to live in a rich, beautiful, and sometimes terrifying universe. It's hard to think of a time when we needed that kind of shared map more. Today, we face a series of existential challenges like global warming that, as Einstein noted, can't be solved with the logic that created them. The old logic is mechanical, viewing the world as a machine composed of passive things like the balls on a billiard table. Today, it's become unmistakable that with this logic, Western science has unleashed enough energy to tear apart the world that supports us. Yet, despite decades of conferences and treaties, our leaders have been unable to do anything substantial about these challenges. What we need is a new logic, a new shared map that will help us address these challenges. Such a new map is essential because our brains evolved to order what we see and know in terms of a specific symbolic order. As a result, we live in what anthropologist Terence Deacon describes as a virtual reality, where our symbols define the world we experience. In pre-modern societies, myth communicated our symbolic orders. Today, science does. And what we need now is a new, more appropriate symbolic scientific order so that we can understand how to deal with our challenges. Fortunately, scientific advances in fields ranging from physics to paleoanthropology have also revolutionized our understanding of the world. That shift is grounded in Einstein's theory of relativity, where E equals mc squared suggests that matter is a form of energy. Or as quantum biologist Mei-Wan Ho puts it, matter exists as domains of energy storage systems. The world, we have learned, is not composed of solid passive things, as our old mechanical worldview insists, but of dynamic energy systems continually responding to the changes around them. This dynamic worldview, which we see in complexity science, represents a different way of ordering our reality. In this paper, I want to draw on complexity science to examine the implications of this shift in worldviews on big history's origin story. Integrating big history and complexity science makes perfect sense because they're complementary disciplines. Complexity science studies the patterns that emerge as energy storage systems evolve, and big history explores the story that has unfolded during this evolution. As I hope to show, thinking about these two together leads to some interesting directions. To examine them, I want to discuss three issues: how complexity science portrays our world as a nested network of energy storage systems, the fundamental patterns that it suggests all evolving systems follow, and insights available when we look at big history through the lens of complexity science. Before I do, I want to briefly summarize how the mechanical symbolic order teaches us to see the universe. With it, reality is composed of solid, independent things that respond to other things in causal chains, just as one gear in Big Ben drives the next. Because these things are passive, driven by invariable laws of nature, events unfold deterministically, as one thing responds predictably to another. This is the logic that most of our social institutions are still grounded in. So we use it to structure the virtual reality our brains construct for us. But this way of thinking about the world emerged before scientists realized that matter is a form of energy, and the newer way of thinking about the universe suggests that our world is structured very differently. Complexity science portrays reality as a nested network of material systems. Your body is such a nested network of organ systems, such as your respiratory system, which in turn is a network of organs like your lungs. Your lungs are a network of groups of cells, and each cell group is a network of cells. Similarly, each cell is a network of smaller structures, organelles, which are further networked from macromolecules like DNA and progressively molecules, atoms, and quantum particles. To be healthy, your body needs the cooperation of structures at all these scales. So to produce energy, your body needs the iron in your red blood cells to pick up oxygen in the lungs, travel through your circulatory system, and drop the oxygen off at a cell. This is a perfect example of why we talk about these as complex systems. As Greg Henriquez points out, there are roughly 3 varieties of complex systems. I know I'm oversimplifying a lot, but you'll get the idea. Among material systems, quantum particles are networked in atoms, atoms in molecules, and molecules in more complex, often larger structures, all the way up to planets, solar systems, and galaxies. Among living systems, molecules combine to form macromolecules like DNA, macromolecules to form cells, cells to form organs, and then organisms. And among human cultural systems, small groups combine, forming progressively larger, more complex societies. More on this later. At each more extensive scale, these systems develop new capabilities. Complexity science calls these networks complex systems. Well, this has been a difficult term to define. I think that the example of our bodies makes it clear that complex systems are composed of many different component systems, often on many scales, and that they have access to the information they need to adapt to and innovate in the changing world they're part of. At each scale, we can examine these complex systems in 3 ways: as a functioning whole, as a component in a functioning whole, or as the environment for other systems. At the scale of each functioning whole, the behavior of the components creates the behavior of the whole, the nature of the whole limits the behavior of the parts, and the conditions of the environment shape the nature of the whole. As a result, to study the behavior of a family, we must also study the behavior of each member in their interactions and the environment of the communities in which they are grounded. Most physicists agree that at the scale of atoms and molecules, their ability to respond to the world is fairly mechanical. However, those physicists also agree that starting at the scale of macromolecules, complex systems can develop the ability to learn and adapt. At this point, they become complex adaptive systems, full-fledged decision-making agents. For instance, certain networks of nerves in the brain can choose to filter out objects that are sensed so they don't appear in conscious perception. From this perspective, events unfold as agent networks at many scales adapt to the changes in other networks, sometimes cascading to produce surprising results. We saw that up close in the recent COVID pandemic, where a change in the genetic macromolecules of a virus in China quickly spread across the globe, partly because Chinese officials tried to hide it, causing extensive social, economic, and political damage across our world. With so many systems making choices and interacting, prediction of such complex systems is dangerous, especially of the future. Our world, then, is a deeply interconnected, nested network of energy storage systems, so it's no longer necessary for mystics to pray to be made one with the universe. On an atomic scale, there is no you and me, only a single, immensely complex network of atoms. But it isn't just the structure of the universe that differs. Evolution also becomes more dynamic as these energy systems, embodied as matter, oscillate between periods when they are stable, acting from long-held habits, and those when they are transforming themselves through experimenting with alternatives. In school, I'd learned that evolution occurred gradually, one random mutation at a time, in chains of cause and effect. For example, our species evolved in a change of precursors, one leading inexorably to the next. Australopiths became Homo habilis to Homo erectus, Neanderthals, and then us. With the mechanical symbolic order, human evolution was viewed as a long, gradual slog from primitiveness to perfection, as paleoanthropologists Ian Tattersall and Jeffrey Schwartz put it. But in recent decades, scientists realized that human evolution wasn't so linear, that evolution seemed more like life struggling to find its way in a continually changing world, or as Tattersall and Schwartz put it, a history of experimentation, of constant exploration of the very many ways there are to be hominid. This form of evolution follows a pattern alternating stable and dynamic periods. Here's the back of the cocktail napkin diagram I drew when I was thinking about this conception of evolution. Some of you will recognize this figure as punctuated equilibrium, the theory Niles Eldredge and Stephen Jay Gould developed to explain the evolutionary jumps that follow mass extinctions. I call it the cycle of an attractor. By the way, an attractor is a term from higher math that complexity scientists use to indicate those behaviors among all possible behaviors that a complex system tends to evolve toward in a particular set of conditions. To put it another way, an attractor defines a system's habitual behaviors, its default responses in its environment. For instance, when you throw a chunk of ice into a pot and heat it on a stove, it will cycle through 3 phases: solid, liquid, and gas. At first, it will remain ice until it approaches the melting point and becomes turbulent and turns into liquid. It then remains liquid until it approaches the boiling point, again becomes turbulent, and turns into gas. Or considered what happened when Earth was struck by a comet about 65 million years ago. For more than 100 million years, Earth's ecosystems were dominated by dinosaurs, but the comet decimated those ecosystems, driving them into a 10 million year phase transition, leading to the dominance of mammals. Similar dynamics appear in market cycles of boom and bust, or in human development, where a stable childhood personality is interrupted by adolescence, leading to a stable adult personality, often ended by a midlife crisis. Similarly, dominant human and social structure has cycled through periods of hunter-gatherer bands, pre-axial agricultural kingdoms, and vast empires punctuated by the Neolithic Revolution, the Axial Age, and modernity. The dynamics of this pattern are driven by the interaction of component complex systems. Toward the end of the stable state, the component systems have a long successful history of following a limited number of all possible behaviors. Their survival had depended on interacting successfully with other component systems whose behaviors may have had an equally long history. As conditions shift over time, new challenges are likely to emerge, yet the old habitual behaviors which allowed them to survive are likely to continue in a period biologist Stan Salt calls senescence, until some kind of catastrophe reinvents the environment and breaks the hold of the old attractor, and a phase transition begins. In the phase transition, these components, free of the constraints of the old attractor, experiment with new behaviors which they may be able to succeed in their new conditions. Those experimental behaviors may be entirely new. Those are the downward strokes moving forward in time, or the reintroduction of old behaviors, the upward strokes that appear to be going backward in time, which of course is impossible. But I wanted to suggest that component systems don't merely innovate. They also try out old experiments that may not have been successful. Finally, when the component systems find the range of behaviors that do work in current conditions, their interactions will develop a new attractor for the system as a whole. One advantage of incorporating complexity science into big history is the way it helps explain the world today. After decades of extremely rapid change, societies across the globe are in a phase transition. As we watch political developments around the world, it's clear that old agreed upon limits to behavior, our behavioral attractors, are no longer observed. In just about every institution in every society, people seem to recognize, mostly unconsciously, that those old ways don't work, but that no one knows what the new ways will be. Most of them are understandably terrified, and the result is a sort of global psychosis. So what might we learn from applying these complexity patterns to big history? For one thing, it will allow big history's origin story to explain that ours isn't the first time when societies around the world have faced existential challenges. Both the Neolithic Revolution and the Axial Age were times of massive social experiment as their societies reinvented their shared symbolic orders. And because pre-modern societies communicate their symbolic orders in myth, Those that succeeded in reinventing themselves almost always did so by rewriting that myth, as Axial Age Greek myth transformed from stories about the gods of Olympus to the mythic philosophy of Plato and Aristotle. Using complexity science, we can think of these symbolic orders as the attractors that hold our societies together. By focusing on the experience of societies that did reinvent themselves, our origin story can create the map for how we can similarly transform the way we think about the world. For example, it can emphasize the interconnectedness of our world so that people are better prepared to understand the cascading effects of their actions in causing phenomena such as global warming. Remember, our reliance on symbolic order results in our experiencing the world as virtual realities that reflect those orders. So the shared maps we make, mythic or scientific, are critical in our ability as individuals and as societies to address all our changes. For nearly 200 years now, our society has thrived with its mechanical symbolic order. But today, it's created challenges that just can't be addressed mechanically. What we need, as we live through a global phase transition, is the shared map for a new symbolic order. Building that new shared map is going on throughout our society today. In fact, I believe we're participating in that process in this workshop. And I hope my comments have demonstrated why I think integrating big history with complexity science will strengthen our efforts to realize David Christian's vision and maybe even understand and address the existential challenges we face today. Thank you. I can't tell you how much I have appreciated this opportunity.